Hi, everybody. Thank you for joining us. We'll go ahead and get started in a minute. We're just going to let people get logged into the system here. So thank you for taking the time to be part of the webinar tonight. All right. Welcome, everybody. I'm Dr. John Lohr, and this is a Thinking Thursday webinar. And I'm super excited because um, not only is on a topic that I really love, and that's astronomy, but it also means I get to hear from probably two of my favorite people in all the Science Olympiad because every time I listen to them talk, I always end up learning something new. So I'm super excited that you're going to get to interact with Donna Young and Conor Todd from NASA. Also joining me on the screens is my colleague Dan Nichols from the National Office. Um, if you would please, so we kind of get an idea of who's here and schools and states, go ahead and put your name. First name's fine, your school or your team, and what state you guys are coming in here from. And while you do that, I want to touch on a couple of housekeeping things. Um, Most importantly, so everybody knows, this will be recorded, and you should have heard the announcement that it's getting recorded when you logged in. We'll send you out a copy of the video, plus we'll post it up on the Science Olympiad YouTube channel, so you'll have access to this afterwards. Secondly, the focus of this webinar is really on helping you guys understand content associated with Reach for the Stars. So about stellar evolution, about some of the objects that are listed this year. So to that end, feel free to put questions either using the question and answer feature, or you can put questions in the chat if you would like. And we will try and get to everything we can by the end of the evening. And if there's nothing that covers all my stuff, so I'm going to go ahead and stop sharing and turn it over to our wonderful expert from NASA, Miss Donna Young, and the lead speaker for tonight, Conor Todd. And if, by way of background, if you haven't gotten to interact with Conor before or seen him present, Conor currently is a systems engineer on the James Webb Space Telescope. So he's one of the individuals responsible for making sure we get the fantastic images every couple of months that are just incredible what they're able to produce. So, Conor, feel free to take it away.
Certainly. Thanks for the glowing introduction. Well, it's nice to meet everybody virtually. I hope you're all doing really well. Yeah, so I'm working for the Space Telescope Science Institute right now, which is contracted with NASA to be Science Operations Center for James Webb. I did Science Olympiad when I was in high school. I competed in the astronomy event. And I've been working with Donna, who has been our fearless leader on all aspects of space science event wizardry for many, many years now. I'm really fortunate to work with her. She is truly the master of this event and has been here longer than just about anybody else.
Be careful how long you say.
I would never. I would never.
Okay.
Yeah, it's really nice to be here. I'm excited to see so many people are attending. And as I understand it, John, this is going to be mostly a question and answer session for me to speak a little bit about the event.
Yeah. And we got our first question in here, and it comes from Elvira, and it's a specific question. So they say in section A, so I'm assuming it's section it's going to be 3A, and it's XIV, so that's 14 if I remember correct.
Yep.
It says Volans, and the question is, why is J122051 plus the 491255? What's the deal with the plus, and what's the meaning behind that?
So what you're looking at in this object. And this is something that you see in a lot of objects that are either very recently discovered, have not had a chance to be super well studied, but have been noticed in scientific papers or by teams and investigators who are looking into these objects for whatever reason. If there's no formal name attached to the object, it will often be given a placeholder designation when it's first discovered. So, in the same way that when we're looking on the surface of the Earth, we have latitude and longitude as a way of describing coordinates. And if you're in Paris, France, the Eiffel Tower is at the exact same coordinates all the time, no matter how the Earth is turning, no matter what time of day it is, no matter what time of year it is. The Eiffel Tower is always in the same place because it's at the same coordinates. And what you can imagine is you can imagine doing the reverse and looking at the night sky. And instead of longitude and latitude, you have what astronomers call right ascension and declination. And the idea here is exactly the same. If you are at a stationary point on the Earth and you look up at the night sky, the constellations and the stars are always going to be moving. There's always going to be a rotation of the Earth, and things are not going to be in the exact same location at a moment-to-moment basis if you were looking at them outside of that reference frame. But if you are on the reference frame where everything is tracked based on the equator and based on how that projects out onto the celestial plane, then you can use right ascension and declination as a means of kind of fixing points in the sky. This is based on where constellations are relative to one another. It's based on where the ecliptic is relative to itself, which is the projection of the path that the Earth travels around the sun on the night sky. So even though these points shift in the night sky relative to your position on Earth, they don't shift relative to each other in the same way that the Eiffel Tower doesn't move relative to the rest of Paris. It's all fixed on the same point. So what you're looking at with an object like J122051 plus 45.1255, what you're looking at is an object whose designation is given in the coordinates, the right ascension and declination. So that's what those numbers indicate, and they indicate positioning because the object itself is either newly discovered or it is very recently identified or it's been known about for a while, but there just hasn't been a name given to it.
Okay. Then can I just ask my own follow-up? You talk about, so is the first number the right ascension, and then the second number then represents a declination?
Yes, I believe that's how this one's written.
Okay.
Yeah.
Yes.
And then, all right, one more on that one is, so I know because going through and working with you guys and heading the rules, I know there's a lot of pluses. Can that declination also be a minus, or is it always going to be a positive value?
It can be both.
Okay.
It can be both.
Awesome.
Above the equator, below the equator, positive,
Yep.
negative.
Okay.
In the same way that longitude or latitude, you could have
Yes.
a latitude of 30 degrees north, or you could have a latitude of 30 degrees south. You can think of the plus and minuses doing a similar thing.
Okay. So again, I mean, if I was looking for those numbers, I would expect to see, like, if I was looking up a star that represents the Southern Cross, it would be negative, whatever the numbers are.
That's correct.
All right.
Yes.
All right. Thank you, guys. And Elvira says thank you as well. All right. So we had a couple students who have typed into the Q&A, and this one I believe is Armand. I hope I'm getting that one right. In a recent test, they received a question that was an HR diagram, but on the diagram, it had a line that moved all around the diagram. He says, or they say it was supposed to represent the evolution of a single star. Their big question about it is, all right, so what does that line called? And it's, I think, really what they're trying to figure out, or like, how would you describe that line?
So it's unfortunately that's one of those questions that I would have to see the diagram itself to give you a completely firm answer on. That could be referring to a number of things. If, for example, it's a line which shows the track of a star before it's on the main sequence, so a pre-main sequence star, it might be a Hennier track or a Hayashi track, depending on the mass of the star. If it is the path of a star through its entire motion on the HR diagram, it might just be a line that somebody drew in there as a means of showing the path of the star itself. Usually, these are lines that are designated by the masses of stars. Stars traveling along the HR diagram. We use the word travel here to indicate that their position is changing. Because what the HR diagram really is it is a way of plotting a star's temperature with respect to its luminosity, or its spectral class relative to its luminosity, or its spectral class relative to its radius. All of these properties are interlinked with one another, and if you know one and you know the other, then you can plot its position on the HR diagram. And what we see is that stars fall into certain regimes. A star that's on the main sequence, depending on what its temperature is going to follow along a relatively narrow band, starting from like the top left down to the bottom right of the HR diagram. Generally, if you're a main sequence star with a very high temperature, you can have a very high luminosity at a logarithmic scale. And then if you're a very low temperature star, you'll have lower luminosity at a log scale. And if a star is going to be of any given luminosity and temperature, it's going to be at a certain place on the HR diagram. So this largely depends on what the HR diagram itself was trying to show you. If it was pre-main sequence, then it was probably a Hayashi or Henya track. If it was the full evolution of the star, it was probably a more general arrow or path showing movement.
So I got a little more information on this. They say that it had sections that talked about submassive stage, asymptomatic stage, and there were a couple others.
Asymptotic?
What?
Asymptotic.
Asymptomatic. Yeah, sorry.
Okay. No, it's all good. Those would refer to different stages of a star's evolution. You'll be on the main sequence. If, for example, you're a sun-like star, you'll be on the main sequence, and then you'll be on the horizontal branch, and then you'll be a giant. More massive stars might become asymptotic giants, which are bigger, more luminous. And then these refer to different stages of evolution of different stars.
Okay. All right. He says they say thank you. All right. So this one comes in from Benjamin, and it's a question about NGC 3324. Right? And getting real, he's getting it, like, I guess, conflicting information. He'd like to know, would you consider that an open cluster? Because he's also found sources that talk about it as a molecular cloud or nebula, and he's even seen stuff that talk about it as part of being part of the Carina Nebula.
Correct.
Yep. They're all right.
Yep. So what you're looking at here is you're talking about a supercategory and a subcategory, and some of the difficulties with categorizing celestial objects in general, objects in the night sky, deep sky objects. So when you're talking about what an object is, an open cluster refers to the stars inside of the object, and the nebula generally refers to the gas, is one very general way of thinking of it. An open cluster can produce a nebula around it, for example, because the cluster of stars the cluster of stars all together are maybe very bright, very luminous. They are heating up the gas and the dust that is around the cloud. If they're really young stars, they might have formed out of a molecular cloud, and parts of the cloud might still exist, even though some parts have condensed into a cluster of stars. So when astronomers categorize objects, if they're describing the entire object, that might encompass a portion of it which is an open cluster, and that's referring to the stars. It might also encompass part of it that is referring to the nebula created by those stars, giving off light and heat, ionizing all of the particles in that cloud that still exists around them. In the specific case of NGC 3324, so NGC 3324 is an open cluster. The constellation it's in is Carina, and the Carina Nebula is a nebula that's associated to the open cluster, but it has a slightly different designation. So the cluster, which is the stars, is NGC 3324. The Carina Nebula, which is the nebula associated with that cluster, is NGC 3372. So the numbers are very close because they were cataloged very close to one another. NGC stands for New General Catalog. It's a way of cataloging objects in the night sky. But they are technically two distinct things. Oftentimes, they will be seen in concert with one another because they are so closely linked as objects. Um, but if you want to be very specific, then NGC 3324 refers to just the open cluster, which is the stars.
Okay. Thank you, sir. All right. We're gonna let's see. This one comes in and it's a question about an image. And hopefully you guys are familiar with the image. And the object is, again, we're back to J122.051 plus 491255.
Yep.
And they're saying that on the NASA page that there's an image of the object. But then right next to the I guess that object, there seems to be a second one that has two red dots,
Mhm.
right? Do you have any idea what those other objects in the back, kind of in the background might be? Or,
So if I'm remembering this picture right, naturally, I just pulled up the press release for this image. So if I'm looking at the same picture that you are, actually, I could. Do I have screen sharing capabilities?
you do.
Okay, then let me pull that up, and I presume that this is the image that you're looking at, right? This one? Yeah.
I would assume so. They said it comes from the NASA page. Um, and they're interested in the two red objects off to the side.
Okay. Um, you can see my tabs that I had up there in the top corner to make sure that I wasn't saying anything egregiously wrong. Um, so we've got if this is the image that you're referring to, then these are two different galaxies. And that one on the left is the one that I want students to be familiar with.
Okay.
That's the green pea galaxy imaged by the SDSS survey. That one over there on the right is another galaxy which is contained behind this other object called S Max 0723. So this is one of those objects that when you're studying it, you need to be careful to make sure that you're studying the right thing here. Because what I specifically want students to be studying here is this one, this green pea galaxy over here on the left, because it is a unique and representative type of galaxy of other galaxies that are like it. Um, Green peas are a specific type of galaxy that is both very, very old. We're talking about galaxies that were forming at the earliest points of the universe. Generally, really small galaxies, but with really high rates of star formation. And what we see in a lot of older galaxies, really old galaxies at the edges of the visible universe, the observable universe, is that these galaxies are not of the same type that like the Milky Way or the Andromeda Galaxy is. And when we see galaxies that have really active star formation, they are generally younger galaxies, galaxies that are dense with a lot of molecular clouds, dust, and oftentimes galaxies that have some kind of gravitational interaction happening between them. Like you'll see often, I think, for example, one of the objects this year, where did you go? I hope I'm not getting this mixed up with astronomy. Um, what we see in a lot of galaxies. Here we go. Stephan's quintet. Thank you. What we see in, for example, Stephan's quintet is we see galaxies that are gravitationally interacting with one another, and the interaction of the galaxies causes their gas and dust to be in collision and accumulation with one another, and that can trigger a lot of star formation. What's interesting about a green pea galaxy like this one, this J with all the numbers, is that as far as we can tell, that's not what's happening. This is a galaxy that is very, very old, formed at the early stages of the universe, and which the light that we see coming from it is indicative of star formation under some process that we're not familiar with. And by we, I mean astronomers, scientists who study this field. So we're looking at what's generally considered to be pretty unexpected prior to recent decades where we started to get really good pictures of distant galaxies, it was assumed that this level of star formation wouldn't be happening. If you look at the general progression of the history of the universe from the Big Bang, you start to see that galaxies at the beginning take a long time to form because everything is so hot and scattered. And then after the galaxies form, then you start to see the stars forming, and that takes some amount of time. What we're seeing now is that some of that might have been happening at a much shorter time scale, the gap between the formation of galaxies and the formation of stars, and it might have even been happening simultaneously. So this is a very burgeoning field of astronomy, and that's why when you study objects in this field of astronomy, you're talking about objects that are either brand new on the cutting edge and haven't really been given time to have like nice names assigned to them yet. But to come back to your question, what we're talking about here is we are talking not about these little red galaxies, but this one in particular right here on this press release is the galaxy that I want students to be studying and learn as much about as they can.
Awesome. Thank you, sir. All right. Let me see. Here we go. So this one comes in from our Navi and our Aeronavi. It's a kind of a content question. So the way they
Okay.
phrased it was, will we be asked general knowledge questions on the test that do not relate to the deep sky objects listed on the rules page? And if so, like what kind of general knowledge might they be
Mm.
expected to have to worry about?
So this is covered by Section 3B of the rules. Participants will be required to demonstrate their knowledge of star formation and early stage evolution by answering questions pertaining to the following topics. So all of the topics that are listed under Part 3B are fair game for general knowledge questions. And these cover a range of different topics, but they all come back to stellar evolution and star formation in some capacity. And this is probably a good time for me to get on my soapbox about the deep sky objects themselves and kind of how and why you should be studying these objects in particular. So when we develop the rules for any given year for Reach for the Stars, and this applies for astronomy as well, we choose a topic for that year to be based around. This year for Reach for the Stars, that topic is the formation and early stage evolution of stars. So star formation, three main sequence generally, their evolution. And then in astronomy right now, we are doing exoplanets, we are doing planetary formation, planetary system formation. And there's a certain set of general knowledge that competitors are expected to have that relates back to that topic in particular. After we've got that topic set, we choose our objects based on that topic. So the objects that we have listed here in Section 3A, those deep sky objects, those are not objects that were chosen just out of a hat randomly because we thought that they looked cool. We chose those objects because all of them are in some way intimately related with the topic of the event. Maybe they are representative or prototypical of certain types of objects or stages of evolution. Like T-Tauri, for example. T-Tauri is one object that's on the list this year, which is the namesake of an entire class of three main sequence variable stars called T-Tauri stars. So it's a very important object to understand for that reason. FU Orionis is similar. It is the prototype of FU Orionis variables. Other objects we chose maybe not because they're prototypical, but because they are in some way unique or superlative or demonstrably interesting. Like, for example, that green pea galaxy I was just talking about, that J with all the numbers. That one was chosen because it's atypical. That one is an object that's worth studying not because it gives us a lot of insight into the general knowledge of other objects that are like it because it's so prototypical, but because it's so different. And sometimes you can learn an area of knowledge by studying case studies that are exactly like that thing or that are representative of it, that cover a lot of the bases. And sometimes you can learn a lot about something by learning about the edge cases, by covering knowledge-wise all of the aspects that are really unique and not typical of that kind of object. So all the objects that are on the list this year were chosen because they are either very typical of aspects of general knowledge that we want students to be familiar with, or for the opposite reason, because they're atypical and they're worth studying for that reason. So keep that in your head while you or your team are studying these objects, is that the general knowledge is not a separate component of the exam from the objects. It's not just you study these objects and you study the general knowledge, and those are separate. The objects and the general knowledge tie into one another. They influence each other. Why they're there has to do with one another. And you're going to be expected to know why it is these objects, not just they look the way they do or are the way they are in particular, but what that implies about their relationship to the general knowledge of the event in general. What are the next stages of evolution? How are these different from other stars like them? How are they different from other nebulas like them? If this nebula were to collapse, would it form an open cluster? Would it be a nebula that only forms one or two stars? How massive would the stars be? What would the stars have in their component spectra? That kind of thing.
All right. No, really
Those last
helpful.
couple questions were a bit more advanced. I would
Yeah.
expect that to be like a regional level or invitation level question.
Okay.
But that's the sort of thing I'm talking about at the higher level.
No, it's really helpful, and you've given me a whole bunch of questions I want to ask, but I'm going to stick with what the attendees have been throwing out there because
I'll stick along on when it's all over, John. I'll hang out.
exactly we'll have to find some time at nationals. So this question is about there's a line in the rules that talks about that the kids should study the scientific and engineering design principles associated with observatories such as JWST, Hubble, Spitzer. Right. So their fundamental question is, what's that mean exactly, and
Sure.
what should they be looking to study specifically?
So I'm just going to lay my cards on the table. This is a relatively new thing that we've been doing in the B Division space science events for a couple years now, and this is 100% my fault. I intentionally put this in here because I think it's important for students to gain some context as they are studying this event to understand how it is that space science happens and what the process of that looks like. Everything we know about the universe, we know because at some point or another, a person or a team of people pointed a telescope at the sky and looked at something for some amount of time. A long time ago, it was just ground-based telescopes with the naked eye, and then as we got more advanced, we started doing it on the ground with radio telescopes, and we started doing it with longer wavelength telescopes, infrared telescopes, and then we realized that if you put a telescope in space, you get around that whole atmospheric problem, and you can start studying things from space without the atmosphere in the way. And then we have the Hubble Space Telescope. Then you have missions like Chandra, which looks at things in the X-ray. You look at the James Webb Telescope that I worked on, which is looking at things in infrared. And you start to see why astronomy gets done the way it gets done, and you start to understand why wavelength distinctions become so important. So this whole section in the rules, the scientific and engineering design principles, the reason this is in the rules and the reason why this is important to a general knowledge understanding of the event is because the way that we do science is fundamentally influenced by the instruments that we have to do that science and vice versa. So to give you a peek behind what my day job looks like, when NASA wants the mission to do a certain thing, when it wants it to take a certain kind of observation in a certain regime of the electromagnetic spectrum, or when it wants to leave a certain amount of time in its momentum management to capture a certain region of the sky, they write up science requirements that say the telescope shall be able to do this kind of science. And that's usually informed by the decadal survey that is managed by NASA. NASA sends it out every 10 years that says, here's all the science we want to do for the next 10 years. And that's informed by astronomers from, all over the place. So the decadal survey sets the science. And that science that's set in the survey turns into requirements that the mission has to be able to meet. And then those requirements get turned into engineering requirements. NASA says, hey, we've talked to all the scientists and they want their fancy toy to be able to do this kind of science. Can you build this? And then the engineers say, yes, we can. Here is what the system has to be engineered to do in order to meet those science requirements. So there's this interplay between why a system is designed the way that it is and what kind of science influences that. So to give an example, the James Webb Space Telescope is a telescope that is in space, not in orbit around the Earth. It's at the Lagrange 2 point, which is a point where the gravity of the Earth and the sun cancel out with angular momentum. The centripetal force of its orbit inside of the solar system in general. And it is a telescope that images in the infrared wavelength primarily, mostly in the near to mid infrared range. You're talking about like a couple, the high hundreds of nanometers into the millimeters wavelength range. Did I say millimeters? Yeah, millimeters. And that is because the telescope is designed under the scientific requirement that it be able to image a very distant objects at the furthest reaches of the the universe, objects at the furthest reaches of the universe, and also that be able to image exoplanets. And that means that infrared light is very important because infrared light can travel a very long time while still not attenuating or losing the energy that it was originally delivered with. So if you know how to do your redshift calculations from the expansion of the universe, which you don't need to worry about, you can get all of or most of the data that you'd be able to get if you were just like looking at it up close. Ideally, if the telescope is good. So infrared light is really good for looking very far away, and it's also really good at looking through clouds of dust and gas to see what's inside. So if you're trying to find an exoplanet, it could be that that exoplanet is in the process of forming or has been forming for a while, but there's still a lot of gas and dust in the way from what it's all forming out of. And being able to look through that cloud of gas and dust allows you to see more precisely what the component characteristics of that exoplanet or the exoplanet system are. So the science is we need to look very far away. We need to study exoplanets. We need to study early star formation. The engineering is the telescope must be in space. It must be imaging in the infrared because that's sensitive to the kind of thermal radiation that you're looking at. And because it's sensitive to thermal radiation, it needs to be orbiting away from the Earth so that the Earth's heat doesn't affect it. And it needs to be pointed away from the sun so the sun's heat doesn't affect it. And that's how you get that really cool looking pink sun shield that blocks out all the light from the sun as it moves around. So science requirements, image very far away, image exoplanets. Engineering requirements, image in the infrared, be in space, have a sun shield pointed away from the sun. And this is how astronomy happens. If you have a telescope that can look in the infrared and can look at that very high distance, very far away distance, then the kind of science that you do with that telescope is going to be fundamentally different than the kind of science you would do with a Mars rover. Because a Mars rover is built to get really up close and personal with the geology of a single planet. You would never ask James Webb to do what the Perseverance rover does, and vice versa. You could never take one of the cameras on the Perseverance rover, point it at the sky, and say, hey, what's the furthest away galaxy you can see? Because it can't. It's not designed to do that. It's designed to do its science, and James Webb is designed to do its science. So the needs of scientists inform the decisions that engineers make, and the design of those observatories is intimately linked to the kind of science that they do, and that's how astronomy gets done. And what we want students to be aware of is not just the idea that stars and galaxies and nebulas exist and are very cool and very beautiful and can be studied in these ways, but we want them to understand why they are studied the way they are and how principles of engineering design work their way into how science gets done, what kind of limitations that imposes, how that necessitates multiple telescopes that image in different regimes of the electromagnetic spectrum, and why scientists would want to use a particular telescope to look at a particular kind of object.
Okay. No, and again, you've added more questions to mine, but it's also a perfect lead in to this one. And this is kind of a technical question, I think, that relates to science and engineering. And that's, how do you tell what frequency an image is taken at? And then how would you know, like, which telescope, which observatory? How do you can you match that stuff up?
So this is one of those things that is partially just uh, studying the observatories themselves and knowing what wavelengths they image in. And part of it is also knowing how to recognize certain characteristics in certain images, and what they tend to have in common and different from one another. You see enough visible light images, and they look fundamentally different from an X-ray image, because an X-ray image is going to be looking at very high energy events, usually isolated to one or two points of extreme energy, things like supernovas, things like the accretion disks around black holes, things like really, really active star forming regions where there's just thousands of extremely hot and bright stars that are very high energy. Whereas an infrared image, you're going to capture a lot of light like that because more things radiate at infrared than at X-ray. So you can just, more stuff will show up in the frame of your image. For all of the observatories that we have on this year's rules, all of them were chosen because they more or less cover the full range of the kinds of wavelength regimes we're talking about here. So James Webb is a telescope that images in the near to mid infrared and exclusively in that range. Hubble mostly images in visible light, like the kind of light that you and I can see with our naked eye, but it also does some infrared imaging and some ultraviolet imaging, which are like immediately to the higher and lower wavelength side of visible light. The Spitzer Space Telescope, again, was an infrared-only telescope. The Chandra X-ray telescope, Chandra X-ray Observatory, is an X-ray observatory. The Roman Space Telescope is going to be a visible light telescope. ALMA it's the Atacama Large Millimeter Array. It's in Atacama in Chile, and that is, a millimeter array. So we're talking about like infrared, microwave to radio. And then VLA, the Very Large Array in New Mexico, is also a ground-based radio telescope. So there is a certain degree of this that is just memorization. You see enough pictures of the same object, and you recognize, okay, not only is that a picture of H.L. Torrey, but that's the specific picture of H.L. Torrey that was taken by ALMA and is a very famous picture. So I know that it was taken in, the millimeter wavelength regime. So like we're talking microwave to radio regime, or maybe like a far infrared kind of thing. Some of it is just memorization. Some of it is recognizing kinds of images that telescope is prone to taking. Chandra images just look fundamentally different from James Webb images. James Webb images just look fundamentally different from Hubble images. A lot of that comes down to studying the missions and studying the images and becoming acquainted with what distinguishes images in different wavelengths. There's not one single thing that you can see and be like, oh, because this image shows a star and it's blue, it is automatically an X-ray image. It could be that it's color graded to blue. It could be that Hubble had one of its blue filters on and it's actually an optical image. A lot of it is learning to recognize patterns. And for most tests that are asking you to isolate, what wavelength that image was taken in, it's usually going to be because that wavelength is relevant to how we study the object. If an object was taken in infrared wavelength, there will probably be a follow-up question that's like, how does imaging in infrared allow us to see into this nebula and to see what's inside? And then the answer would be like, oh, it allows you to see the stars that are inside of this nebula because you're looking past all the gas and the dust to look at the stars, maybe in an open cluster inside the nebula, like REN-GC 3324, like we talked about before. But yeah, that's not one of those things where there is necessarily a correct right and wrong. Like every time you see an image, if it has this, then it's definitely this. But there is a checklist that you can run down. You can see for yourself, hey, do I recognize this image? Do I recognize the observatory that took it? If you recognize that an image is a Chandra image, then you know it was taken in the X-ray, even if you don't have anything that proves X-rayness about the image. I hope that's a helpful question.
No, I think it does. And also, and now, while it's incredibly difficult to predict what is going to occur at over 400 and some tournaments, I also kind of get the sense that if somebody's asking you about that, like, okay, how was that image taken? It's going to be, oh, it was with X-rays, it was with infrared, this is a visible light, as opposed to this is at the, and I'm going to screw the numbers up because it's late in the day, but like 522 nanometers versus, you
Oh
know,
yeah, 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 yeah.
560 or something like that, right? It's
Even
really going to
even
be
at the even at the highest level of competition testing that I write, even all the way at the national level, I would never ask a student what is the nanometer scale of this optical image. What specific number is attached to the wavelength here? I would never expect any student to ever be more granular than optical image, infrared image, X-ray image, unless it's a very important kind of like wavelength, um, unless it's like a hydrogen alpha image, which is a very specific kind of filter that refers to uh, the ionization of a hydrogen atom, which H alpha is, oh God, 1.216 millimeters. Um, H alpha, what is this? Oh, it's 656, not even close. 656 nanometers. So unless it were very particular and specific and famous kind of uh, kind of wavelength line, I would never expect a student to be any more granular than infrared, optical, X-ray, radio, etc.
perfect. All right. Along similar lines, a question comes in about will students need to know any specific formulas or equations for the test?
You will need to be familiar with equations, but you will not be expected to do math, algebra, physics with those equations. And this is something that I definitely want to stress as strongly as I can. This event does not allow students to bring calculators, and tests should reflect that. Students should be familiar with things like Kepler's laws of orbital motion. Students should be familiar with the idea that um, when planets orbit a star, they orbit in an ellipse, and the star sits at the focus, one of the foci of that ellipse. Um, Students should be familiar with what a semi-major axis is, a semi-minor axis, the long and the short axes of a elliptical orbit, respectively. And students should be broadly familiar with the relationships that certain quantities have to one another. For example, in Kepler's third law, there is a relationship between the period and the semi-major axis of a planet orbiting a star, or two stars in a binary system, where one is higher or lower mass. And that relationship is uh, the period to the second power related to the semi-major axis to the third power. So if you increase one by some factor, it will be squared on the period side, and then there's going to need to be a corresponding increase on the semi-major axis side to the third exponent. That is the highest order of math and calculations that any student is ever going to be expected to do. And the reason why it's not calculator derived is because the question here is fundamentally asking, if you increase one quantity, how would you expect the other to change? If you increase a period, how would you expect semi-major axis to change, all things held equal? And the answer is that, oh, the semi-major axis would increase because you've increased the period. They are directly correlated to one another by some exponent factor. You're not going to be asked, for example, the mass of the star is 2.5 solar masses, and there's a planet orbiting with a period of 556 Earth days. Calculate in kilometers the distance from the star to the planet. You're not going to have. There's no calculations. At the very highest levels of competition, students would be expected to be able to give you an answer to, if I doubled the period of this planet, by how much would the semi-major axis increase? And that is the very highest level, because what you're talking about is a factor of, okay, you double the period is scaled to the square, or semi-major axis scaled to the cube power. So you would expect the semi-major axis to increase by a factor of 3/2, doing the exponents.
Okay. Um, so now we're getting a couple. I think couple of people are hitting on this one, and
Mhm.
they're looking for, and they've phrased the question in two ways. One way the question is came in is, hey, there's a lot of stars and constellations. Any particular ones we should focus on? And then the other variation that someone threw in here was, what's the best way to test yourself, memorize, and study the different constellations on the list, as well as the same for the deep sky objects? Any
So I'll answer the
suggestions
first
or
one.
tips?
Oh, sorry.
No, I was just gonna say, any suggestions, tips, like what advice do you have to give the guys?
So I'll start with the first one because this is one that I can answer very quickly. So the only constellations that you're expected to know are the ones that are on this list. You're not going to be expected to identify, for example, Ursa Major. You're not going to be expected to identify. Do I have Sagittarius on here? You're not going to be expected to identify Sagittarius. You're not going to be expected to identify Cepheus. You're not going to be expected to identify constellations if they are not inside of. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 constellations, and I believe 18 objects because some of these are doubled up. You're only going to need to know the locations of the objects within the constellation and what those constellations look like. You would need to know what Orion looks like, and you would need to know where Messier 42 is inside of that constellation. If I gave you a picture of the Orion constellation, and I pointed to a location inside of Orion, I might ask you what object is located where this arrow is pointing. And it might be pointing to Messier 42, which is the Orion Nebula, or it might be pointing to F2 Orionis, or it might be pointing to HOPS 383, and that's it. Because those are the only three objects in the constellation of Orion that are in this year's rules. So if you know what Orion looks like, and you know that there are three objects on the rules this year that are inside of Orion, then you got a 1 in 3 chance of guessing what that object is if you've done no studying of their locations within that constellation. Now, if you wanted to get a little bit more detailed on constellations, and this is kind of more answering the second question, studying the constellations and studying the objects to be more precise about their locations and how to study them. I would recommend there are a couple websites out there. I think if you just look up like night sky tracker or like night sky map, it'll give you a full map of the night sky, which is all the constellations relative to one another. You can either do this in flashcard form where you take the map, and I would recommend doing this yourself because building this yourself is a good way of reinforcing the knowledge. Take that night sky map, start taking screenshots of all different constellations, and take wider and smaller screenshots of those constellations that show just the one constellation with the other constellations bordered up next to each other. Start getting familiar with where they are located relative to one another. Know which constellations border Orion, which ones border Dorado, which ones border Carina. Know what it looks like in the context of a sky map. And then you can also go to Stimbad, I believe, is a database that shows the locations of objects within constellations. And most databases that catalog objects will show their location in the night sky, or at the very least, they will tell you the right ascension and the declination of those objects, as we talked about before. So if you're not able to find a catalog that actually gives you the exact location of the object inside of its constellation as an image, what you can do, and this is a great learning exercise, is you can go find that object's right ascension and declination. Every single object on the list has that information somewhere. You find that number, you go to your sky chart, the one that you pulled up that has the whole map of the night sky, and you follow along. You go to whatever right ascension is that object, and then you go up to the declination, and then you find the location of that object inside of the constellation by following it on a map the same way you would for the latitude and the longitude on the surface of the Earth.
All
I would
right.
strongly recommend taking those pictures yourself, breaking them down yourself, and making yourself flashcards for them to study, either in like a Quizlet or by actually physically printing them out and recycling them.
All right. Hey, Connor, could you say the database you recommended just now?
Simbad, Simbad,
Simbad.
Simbad. And
Simbad.
Simbad is a place where you can look up, at the very least, the galactic, the night sky coordinates of any object on the list. You might have to use a different catalog number than the one given in the rules. Some of these objects have multiple names. Like, for example, if you look up Stefan's quintet, it probably won't return anything. But if you look up the new general catalog numbers of any of the galaxies in that quintet, it'll give you the right ascension and declination based on the new general catalog number.
All right. Um, so then again, kind of building off of content here, we've gotten a couple of questions about um, kind of charts and graph and information on them. So
Mhm.
we'll start with this one, throw it out there is, will they be asked to read and identify objects on star charts? And
Yes,
if so, how do you read it? And there's a specific way to identify the objects. And I think, if I'm wrong, since you clearly said yes, that's going to be an expectation. It kind of sounds like you went through that process already, right? It's going to be,
yes.
you need to know the right ascension and the declination, and kind of,
Yeah, the
and just
coordinates.
in the coordinates, and then know in your head that at these coordinates is, this object. So
Your
it's
star chart should have those coordinates laid out like a grid, the same way that a map of the Earth's surface would have the longitude, and the latitude laid out like a grid. You can do the exact same thing with the star chart. You can follow the right ascension and the declination the same way you would for a map, and you can direct your own finger to that point on the map. What I'd recommend doing is I would recommend, since you're allowed to have cheat sheets taken into the test with you, for every object on the list, I would recommend having somewhere, if you take that object and you put it on your cheat sheet, I would have the coordinates of that object so that if you're given a star chart, you can follow the right ascension and declination and identify it on that chart.
and you're not worried about just remembering it. So
No, no, no. I would absolutely write those numbers down on the cheat sheet and take it in with you. Do not spend your time memorizing numbers. Put numbers on the cheat sheet. Memorize the concepts. Memorize the ideas. Memorize and understand at an intuitive level the difference between a low mass star that stays on the main sequence for a long time and a high mass star that evolves off the main sequence relatively quickly, and what they look like in the early stages of revolution. Understand those sorts of concepts. Leave the constellation names and the right ascensions and declinations and the distances and all that stuff. Put that down. Don't memorize those numbers.
okay. Um, then along the similar lines, apologies on my cough.
Plus,
What kinds of charts? And so we talked about star charts are yes. We've talked about HR diagrams are a definite yes. Are there any other kind of charts and graphs the kids could kind of expect to see on an exam?
so a couple really important ones are going to be things that are not charts but are plots of data. So one of the most important ones to be familiar with is a light curve, which shows you the brightness of any kind of object, usually a star, 99% of the time a star. Although I've seen light curves for exoplanets, they're very cool. But most of the time it's going to be a star. And what it shows you is that star's brightness over time. And light curves are important because they're kind of like fingerprints for certain kinds of stars. There's a type of star called a variable star, which is a star that changes brightness over time. And they can do so periodically. Maybe they'll get bright and then dim and then bright and then dim in a very predictable cycle. Or maybe they'll be variable stars because they get very bright all of a sudden due to some kind of physical process happening, and they stay really bright, or they taper down in brightness back to a quiescent state is the word for when they're not undergoing any kind of major brightening effect. And what these light curves look like is specific to that kind of star. And some of the stars on this list, I'll just give you a hint right here, are T-Tauri stars and Orionis variables. And these are very different kinds of stars because T-Tauri stars are unpredictable in their variability, but they vary within a certain range of brightnesses. And uh, Orionis stars are generally going to be, or Orion variables, sometimes called, are going to be the kinds of stars that are very like normal in their brightness, very steady, and then all of a sudden jump up many orders of magnitude brighter. So being able to read a light curve and to identify the kind of star that is being pictured in that light curve is really important because that can tell you a lot about the kind of object that you're looking at, and it can tell you a lot about what's going on inside of that. And then you should also be familiar with a plot that is, there are two types of plots that you will sometimes see for planets. Now, this is not super important in this event. there are a couple objects in here that are thought to have exoplanets, and you might be given, for example, a diagram of an exoplanet transiting that star, or you might be given a diagram of an exoplanet that's maybe not passing in front of it, eclipsing it the way a transiting exoplanet would, or it might be affecting the what we call the radial velocity of the star, which is its movement towards and away from us. Those are a little bit less important. You might see those at more advanced levels because there are only a couple objects on this list that actually have exoplanets anyway. But being able to read plots of data and information about an object over a period of time is also going to be really important. So in addition to the star charts, the HR diagrams, and potentially the spectra of a star is the last one that I would bring up. A star spectrum is when you look at all of the wavelengths of light that the star is emitting, and you look at where there are certain peaks, and you look at where there are chunks of the spectrum taken out, what we would call absorption lines. And those lines are always coordinated to certain elements, and there are patterns in the spectra that are always the same. If you have a lot of hydrogen in your spectrum, you're always going to have lines at certain locations. That's what that H alpha line I referred to was before. 656 nanometers, there's always a line right there very strongly if there's a lot of hydrogen. That's your H alpha line. If you have carbon, if you have oxygen, if you have helium, these are all elements that are going to create specific fingerprints in the spectrum of the star in the same way that the brightness variation of the star would be a fingerprint of the kind of variable star that it is. So HR diagrams are important. Spectra are important. Star charts are important. And then plots of data concerning the star itself, things like the light curve or things like the planetary transit or radial velocity are also very important to study.
All right. We got to go one more, and then depending on the answer, we may be able to squeeze in one after that if
Sure.
Donna can hang on for a little bit.
Yep.
So this comes from Nathan, and he's very interested in a particular galaxy, NGC 4395, and tells us that it's a Seyfert dwarf galaxy, but it lacks a galactic bulge. And he's really interested in it and would love to focus future research on the galaxy, but he can't really find information despite the it being unique.
Right.
So two things. One, I'm sure he'd love tips on, hey, any places he might go to find additional information and kind of, but also, you guys got any thoughts on why it might lack a galactic bulge?
So I'm not a galactic physicist, and I'll also say up front that this is not an object that's on this year's rules. So everything I'm about to say doesn't have anything to do with the study of this event. And also this year we're not focusing on galaxies. So don't take what I say as having any influence or impact or necessity within the context of this year's event. This is not a galaxy-focused event this year, and NGC 4395 is not a topic in this year's rules. It's not an event to study. So I'm going to answer this quickly because I do want to give time to other questions. I know the galaxy you're talking about, and I'm a little bit familiar with Seyfert galaxies. Like I said, I'm not a galactic physicist. It's dwarf galaxies are generally not going to have the same kind of really pronounced spiral structure that 4395 has. And they tend to be a lot more variable in their size, their distribution, how they look, what their structure is. And if you look into the history of categorization for this galaxy, you'll see that it was eventually Spiral Galaxy, or it was originally called Spiral Galaxy, but then that changed once we learned more about it, because dwarf galaxies just have fundamentally different characteristics from spiral galaxies. Obviously, they're smaller, they have fewer stars, they don't radiate in the same wavelength regimes. I went ahead and I looked this galaxy up, and I see that it's a Seyfert galaxy, but it has a very low mass supermassive black hole. Um, I know that galactic bulges in larger galaxies are, under my knowledge, usually the result of a lot of stars packed in the center of the galaxy, where there's more active star formation. Um, and a lot of times these are going to be areas of very high density, very active star formation, like I said, where there's a lot of very bright and hot and very high energy activity going on. Um, I would be curious if this is mostly a matter of the galaxy being relatively low mass in general, because in order to have a galactic bulge, you need to have a lot of accumulated matter in the central parts of the galaxy. And generally, when you're speaking in astronomical terms, you tend to see this runaway effect, where if you have more mass concentrated in more areas, then things are going to get denser and accumulate further and further up to certain points. This is the theory behind why black holes happen. You just have so much mass concentrated in one area that it starts to become a fundamentally different kind of object. Initial mass functions are a really important aspect of all areas of astronomy. They're important for stars, important for galaxies. They tell you more or less what to generally expect out of an object based on whatever its mass is at the time of its formation. Galaxies that are generally low mass, I would expect not to show as prominent bulges as galaxies that are higher mass, just because there's less material there to work with, there's less gravitational force happening. Um, this is me completely spitballing an answer on the top of my head. Like I said, I'm not a galactic physicist. This is the kind of thing that, Donna, if you have any further thoughts on this, I would encourage you to jump in and tell me what I got wrong, because my best guess is that it has to do with the fact that it is a relatively low mass galaxy as far as safer galaxies go.
That's as much as I know about it. I haven't seen anything about it lately, so.
All right. Then the last one we have is, or last one I should say we have time for, is a question that came in asking about, could you explain a little bit about hydrostatic equilibrium and how, like, I think it applies to what you were talking about, and Don and I were
Mm-hmm.
talking a little earlier about, like, how does that impact the evolution of a star or the appearance of a star?
Yeah, so hydrostatic equilibrium is a general physics term that doesn't just refer to stars, but is really important in the context of stars and within the context of any situation where you have some massive material that is trying to support itself. So when you're talking in the context of astronomy, usually hydrostatic equilibrium refers to a state where you have two forces that are counterbalancing each other. There is the inward pulling force of gravity, which when you have a massive object, there's gravity pulling in. That's what happens with the Earth. That's what happens with the sun. That's why we have planets orbiting the sun. The sun has gravity well. And then you have an outward force, pressure that pushes outward. And that is due to the heat, usually, if it's a star, the heat that results from the nuclear fusion happening inside of the star, or if it's something like a molecular cloud, it's the heat from dust and molecules literally physically rubbing up against each other. Hydrostatic equilibrium is a state that objects fall into when those two forces are balanced. When gravity pulling in cancels out with thermal pressure pushing out. And when that state of equilibrium is compromised, that's when you start to see most of the major effects that we attribute to evolution of stars. So, if you have a molecular cloud that's sitting there in space, it's a bunch of molecules and gas and maybe a little bit of dust in a really big cloud, orders of magnitude larger than the solar system. These can be like light years in diameter sometimes. Um, and if that cloud is stationary and it's not doing anything, it might be in a form of hydrostatic equilibrium. All of the bits of gas and dust are interacting with each other gravitationally. Maybe they're pulling in on each other, but they'll rub against each other, they'll push each other back out, etc. And then maybe near to this cloud, a supernova happens and sends out a shock wave through the medium in between, and it disrupts and pushes against all of these, and it pushes all of the gas and the dust into this like packed in space. All of a sudden, these little bits of molecules and gas and dust are in such close proximity with each other that gravitational laws take over and gravity becomes stronger than the outward pressure of the thermal interaction of this gas and dust. And then you're going to start to have a situation where gravity is just too strong for pressure to hold up against it. Hydrostatic equilibrium has been compromised, and now all of that gas and dust is contracting by gravity into smaller and smaller spaces. And until it gets hot enough, until there's enough outward radiation pressure from all of the heat and thermal energy, it's going to keep collapsing. and that's how you get stars. Stars form when the gas that used to be in equilibrium was disturbed, and the gravitational interactions of all the bits of gas and dust and molecules overcome the radiation or the thermal pressure that was keeping them from collapsing, and is not going to stabilize and go back to equilibrium until the thing that is about to become a star begins to fuse elements in nuclear fusion, start with hydrogen, and then all of a sudden gravity is halted and it's stopped because you're producing so much radiation pressure inside of the star that you can finally exert outwards a strong enough force to counteract gravity. And that's what we call the main sequence, when you are exerting pressure in the form of thermal radiation from fusing hydrogen into the core of star. Once you reestablish hydrostatic equilibrium, pressure pushing outward, balanced by gravity pulling inward through the fusion of hydrogen, you are a main sequence star.
All right. Well, thank you very much. At that note, I think we're going to go ahead and end it. Thank you guys for attending. There's one final question that kind of came in the chat. So everyone will receive a link to the video at your email address you used to register. So and that'll probably happen over the next couple of days. You guys should be getting that link. We have to do a little editing and processing on the video. I'll also make sure that I get the name and the web address of the simulation that Conor talked about, because I know a couple of people had trouble capturing that. So we'll make sure you guys have that. And if you guys just could Conor and Donna and Dan for doing this for us. It's really appreciated. And again, like I have a ton of questions, so we'll have fun talks at Nationals.
I can't wait. Thank you all for being here. I really appreciated the questions. I love talking about this event. I love talking about astronomy, and it's really great to hopefully make things a little bit easier, a little bit clearer for all of you as you're studying and as your competitors are studying. And I wish you luck with the year. I know that we're getting into swing with regional and state competitions, so hopefully I see some of you at nationals down the road.
And I did notice one question that talked about resources and sample tests to use to practice, to prepare. We have been posting some. We only post our own tests that are written by our little group. We call them the A-Team, All Science Olympiad alumni. And some of them we post just so you can use them. If you go to the Chandra website, click on education, and then click on, and when you click on, when you go to Chandra, you click on education, up in the upper left-hand corner, you will see where you go directly to JS9, which you'll be using in Division C. The Science Olympiad webinars are posted there, and we post sample test. We don't have, I think we only have one Reach for the Stars one up there so far. It was the U Texas Division B Reach for the Stars test. We will be posting more and more of those up there as we go along, so complete with the answer key, and just so you can use them for practice.
I put the link to that Chandra page in the webinar chat. I think that everybody can see it, hopefully. So if you follow that link, it'll take you to the website that Donna just talked about.
Yeah, and I'll make sure that gets shared in the follow-up materials as well.
Great.
All right. Thanks, everybody. Attendees, have a wonderful night. Have a wonderful season. And like Conor says, we all hope to see you at a tournament sometime soon. Good night.